So now we're going to start into the most fundamental views of fluid dynamics. And ultimately, we're going to arrive at four equations that can be used to summarize everything we've ever done in here. And so these will be the most fundamental equations of the course. And so they're heavy. This video shows the derivation. And I like derivations because they help me understand through seeing what each term means. But I will create videos as well that just talk through what this equation that we're going to end up with today looks like and how to use it. So rest assured that after I go through this, I'm going to give you lots of examples of how to apply it. So the topic for today is going to be conservation of mass for a finite control volume. Let's get started. All right, so remember, when it comes to dynamics, there are two things that we're really interested in: the conservation of mass and the conservation of momentum. And if we apply these to a fluid element, we can either obtain integral equations or differential equations, and that comes from which kind of control volume we're talking about. So when we use a finite control volume, which is what we're going to do today, we're going to use the conservation of mass on a finite control volume. The result is going to be a set of integral equations. These are very useful equations, widespread application, as you'll see with the examples when we get to those. The way we write a conservation law, remember, is that the rate of change of the conserved quantity is equal to interactions that increase it minus interactions that decrease it. So if we're talking about conserving mass, we can say that the rate of change of mass in our system is equal to the net flow rate of mass going into the system minus the net flow rate of mass going out of the system. These two terms could also just be combined into one term, which is the net flow rate into the system. And if that's positive, then flow is happening in, and if negative, flow is going out. So all this is going to come from a fundamental concept, right? We've done these differential elements for a while now. So let's take our finite volume, which I've got here, the big cube, and look at an infinitesimal version of that, this differential volume dV. We know that the mass in this infinitesimal volume could be written as dm, and it would just be the density times dV. And so if we want the total mass in the system, we simply integrate both sides of this. And so you integrate the left-hand side dm, and it gives you an m. You integrate rho dV over the volume. That's going to become a triple integral of rho dV. And that tells you the mass in the system. Well, that's useful because the first thing that we're trying to build here is the rate of change of mass in the system. So if we find the mass and then take the rate of change of that by taking the derivative with respect to time, as I've done here, you get the rate of change of mass in the system. And so we can build this equation one block at a time. For example, here's the rate of change of mass in the system. We take the mass that we found by integrating rho dV, take the derivative with respect to time, and that gives you this first term. So what's it mean? Well, if you have a positive rate of change of mass in the system, dm dt greater than 0, what that means is that the mass of the system is increasing. This is the proverbial bucket being filled with water or whatever other liquid. All right, so now that we have this first term, let's work on the second term. We want the flow rate going into the system. Okay, so flow rates happen when we cross areas, right? The whole m dot equals rho VA thing. And so what we're going to do is find a differential mass flow going through a differential area on this wall of the tank, which is rho V. Instead of A, it's rho V dA. The first thing I want to point out is that the velocity is a vector, and it could be a 3D vector with lots of components. And the component that we need if we're going to use this concept of rho V dA is the component that is in the direction perpendicular to the area you're talking about. And so we can define the normal vector, which we always define them as pointing out. And so this thing is normal to this surface. And if we take the dot product of the velocity vector with that normal vector, you get the component of the velocity vector that is in that direction that we're interested in. And so we can sub in v dot n for v here, where what I mean is the velocity vector is dotted with the normal vector of that area. and that's still multiplied by rho and dA to give us a differential mass flow dm. Keep in mind that n points out of the system, and so if you get a positive number when you do this dot product, that means that this flow is out of the system. Or if it's a negative number when you do the dot product, that means it's going to be flow into the system. And so if we integrate both sides of this, on the left-hand side we get m dot, and on the right-hand side we get the integral over the area of rho v dot n dA, and now this velocity can vary all you like over the area, so that's nice. And just to keep it clear, this is positive when it's flow out, and so I've put the sign here, or the notation here, to remind us that it's mass flow out. However, if we go back to our fundamental concept, right, we want the rate of change of mass in the system. We got that last time. This is the net flow into the system. That needs to be positive when it's in. And so if this is the flow rate in, the opposite is the flow rate, or I'm sorry, if this is the flow rate out, then the flow rate in is just the negative of that. M dot n equals minus integral of rho v dot n dA. Okay, so let's put these two ideas together. We figured out this term, we figured out this term. Let's smash them together real quick and get our final equation. Okay, so we want rate of change of mass in the system is equal to the net rate of flow into the system, which we built as so. And so we put this term in, we put this term in, we move them. We usually write them on the same side of the equation, and so here it is. And we call this the conservation of mass. It's also called the continuity equation. And this is one of the four most fundamental equations that we're going to see all semester. This is the conservation of mass applied to a control volume. So let's break it down one more time so we make sure we understand here. The integral of rho dV over the volume is the mass. That is the mass in the system. And if I put a d by dt on that, what I'm saying is this is now the rate of change of mass in the system. This integral here you can think of as adding up all of the different rho VAs in the system. We're just adding up all these little mass flows that are going in and out. The reason that this dot product showed up is that the velocity vector can point in any direction at once, but the only part that contributes to the mass flow is the part that is normal to whatever surface you're talking about mass crossing. And so we define these little normal vectors that point out of our system wherever mass crosses it. And so when we do that dot product, remember a dot product gives you a scalar. It's just going to be the velocity magnitude crossing that particular plane. And so this is still just rho v a, right? When we integrate over the area, it gives us the entire rho va.